In this video, I want to look at circulation and flux for more general regions than what we've been looking at so far. We have already seen that Green's theorem works very well when I have simple regions and curves that always run counterclockwise, but not all of the regions and curves we work with are going to be this simple. And it may take some additional creativity and ingenuity to be able to apply Green's theorem to more complicated regions. The following regions are examples of ones that will require a bit more thought. The first region is a half annulus. This looks like the top half of a washer situated so that it's centered on the y-axis above the x-axis. You'll notice that when I start with a counterclockwise orientation on the outer rim of my annulus, that as I move around the outer edge, the vector eventually becomes one that moves clockwise over certain areas of the boundary. The same kind of thing happens with a full annulus, where the outer rim has the counterclockwise orientation, but the inner rim has a clockwise orientation. It's not as complicated as it might seem, as long as we can remember some of the things we've already learned. For example, for many of the more complicated regions that we work with, it's quite likely that it will be much easier to compute circulation or flux if I use cylindrical or spherical coordinates instead. So look for ways that you can take advantage of symmetries when choosing the coordinate system that you're going to use. Let's work an example. If I'm given a vector field specified by f is equal to the vector with components x, y, and r is the half annulus described by the set of all points r theta, such that 1 is less than or equal to r, which is less than or equal to 2, let's compute the circulation on and the outward flux across the boundary of the region. Let's assume the boundary is oriented so that the outer edge of my half annulus runs counterclockwise. But my hint is, don't make this harder than it really is. The circulation using Green's theorem is given by the closed integral over C of f dot dr, which is equal to the double integral over r of the partial of g with respect to x minus the partial of f with respect to y dA. The partial of g with respect to x is 0 here, and the partial of f with respect to y is 0, so that my circulation is the double integral over r of 0 dA, which is 0. This tells me that there is 0 circulation at the boundary, and therefore this particular vector field is an irrotational vector field. Now I want to compute the flux using Green's theorem. The flux is given by the closed integral over C of f dotted with n ds. This is the double integral over r of the partial of f with respect to x plus the partial of g with respect to y dA. The partial of f with respect to x is 1. The partial of g with respect to y is 1. So that this becomes the double integral over r of 2 dA. So that my flux is twice the area of the half annulus. 2 times 1/2 times the quantity 4 pi minus pi gives me 3 pi. Now recall that when we worked with circulation of conservative vector fields, there was a potential function phi that allowed us to write my vector field as del phi, or the gradient of phi, which simplified our work on these vector fields. And it just so happens that the flux in a source-free vector field has an analogous function that we call the stream function. If I'm given a two-dimensional vector field f that has vector components fg that is differentiable on a region R, there may exist a stream function psi or psi that satisfies the following conditions. The partial of psi with respect to y is equal to f. The partial of psi with respect to x is negative g. If I compute the divergence of my vector field, f given by the vector with components fg that has a stream function, and use the fact that psi sub xy is equal to psi sub yx, we get this. The partial of f with respect to x plus the partial of g with respect to y becomes the partial derivative with respect to x of the partial derivative of psi with respect to y plus the partial derivative with respect to y of the negative partial derivative of psi with respect to x, and this is equal to 0 because of the fact that psi sub xy is equal to psi sub yx. This tells us that the existence of a stream function guarantees that the vector field has a zero divergence and is therefore source-free. The converse of this is also true on simply connected regions in R2. The level curves of a stream function are called streamlines. The vector field F is everywhere tangent to the streamlines, so that the graph of streamlines will give us an excellent visual representation of the flow of our vector field. We saw that circulation integrals of conservative vector fields were path independent, and now with these streamlines we see that flux integrals are a source-free field that are also path independent. So here's a side-by-side comparison of the properties of conservative fields and source-free fields. For conservative fields, I have a curl given by the partial of g with respect to x minus the partial of f with respect to y that is equal to 0. In my source-free fields, my divergence is given by the partial of f with respect to x plus the partial of g with respect to y, and that is equal to 0. In conservative fields, my potential function is phi, where f is equal to the gradient of phi, or the partial of phi with respect to x is f, and the partial of phi with respect to y is g. In source-free fields, my stream function is psi, with the partial of psi with respect to y is equal to f, and the partial of psi with respect to x is negative g. In my conservative fields, circulation is given by the closed integral over c of f dot dr, which is equal to 0 on all closed curves c in my region. In source-free fields, my flux is given by the closed integral over c of f dot n ds, which is equal to 0 on all closed curves in c. In my conservative fields, I have path independence because the integral over c of f dot dr is equal to phi of b minus phi of a, the function values evaluated at the endpoints. And in my source-free fields also are path independent because the integral over c of f dot n ds is equal to psi of b minus psi of a. So let's work another example. If I'm given a vector field f is equal to the vector with components y squared, x squared, let's verify that the vector field has zero divergence and then integrate the relations f is equal to phi sub y and g is equal to negative psi sub x to find a stream function for the field. The partial of f with respect to x plus the partial of g with respect to y will give me 0 plus 0 is equal to 0. So that I do have a zero divergence, and this is a source-free field. The partial of psi with respect to y is equal to y squared. This means that psi of xy is equal to the integral of y squared dy, which gives me y cubed over 3 plus a constant of integration that is a function of x. I'll call that c of x, of my new psi with respect to x. I note that my partial of psi with respect to x is given to me as being negative x squared for my vector field. So I'm going to take the partial derivative with respect to x of the psi that I got through integration. This gives me the partial of psi with respect to x is equal to the partial of c with respect to x of x, and that is equal to negative x squared. So that c of x will be the integral of negative x squared dx, which gives me negative x cubed over 3 plus a constant c. Because this constant really is a constant, I'm going to let it be 0, and my stream function psi of xy becomes y cubed over 3 minus x cubed over 3. So now you get to try it. Pause the video, and given the vector field f specified by a vector with components e to the x cosine y and negative e to the x sine y, determine if this is a source-free field, and if it is, find the stream function for the field. When you're ready, restart the video to check your understanding. The first thing I need to do is find the divergence for my field. f of xy, in this case, is e to the x cosine y. G of xy is negative e to the x sine y. The divergence is the partial of f with respect to x plus the partial of g with respect to y, and I know it has to be equal to 0 if this is a source-free field. The partial of f with respect to x is e to the x cosine y. The partial of g with respect to y is negative e to the x cosine y. E to the x cosine y minus e to the x cosine y gives me 0. So I do know, in fact, that this is a source-free field. So now I need to find my stream function. The partial of psi with respect to y is f, and the partial of psi with respect to x is negative g. E to the x cosine y is going to be equal to the partial of psi with respect to y. This tells me that psi of xy is given by the integral of e to the x cosine y dy. This gives me e to the x sine y plus a constant of integration I'll call c of x. If I take the derivative of this integral result, I get negative g is equal to e to the x sine y, which is equal to e to the x sine y plus the partial of c with respect to x of x. Comparing both sides, I see that my partial of c with respect to x of x is 0, which means that my constant of integration is just a constant, and I can let c of xy equal 0. This gives me my stream function described by psi of xy is equal to e to the x times sine y. This is how I can apply Green's theorem to far more general regions. And the key is look for opportunities to use symmetries or to convert to coordinate systems that will make your work easier, but don't make these harder than they are. Be sure and let me know if you have any questions.